Hey, welcome back everyone for third of Massimiliano's lectures. Massimiliano, over to you.
Thank you. So we are in part 2 about topology, the role of topology on thermodynamics. And last time we ended by introducing, I just started topology and I introduced cycles as right null vectors of the stoichiometric matrix. The internal cycles were the ones of the full. All the cycles are the one of the reduced one, because there are more cycles for the reduced one than for the full matrix. And I define the emergent cycle as those missing cycles when going from the internal to all of them. So this is why the number of emergent cycles is the total number of cycles minus the number of internal cycles. They can be expressed, I will use it later, because simply by taking the difference of these n number of internal cycles and number of full cycles as the difference of rank between S and Sx. And then I argued to give you a, wait, first we saw that these two cycles here were cycles of our stoichiometric matrix here, so emergent cycles. And we saw that because we can decompose the steady state flux in terms of cycles, because steady state by definition, when we act with a stoichiometric matrix on it, the derivative of the concentration must be 0. As a result, we could show that when applying the y part of the stoichiometric matrix, which is the lower part, remember this is the Sx part of the stoichiometric matrix, this is the Sy part of the stoichiometric matrix. When acting with a stoichiometric matrix on an emergent cycle, one gets basically the stoichiometry of an effective reaction. And this was illustrated here. So this was the emergent cycle. When acting on the with the stoichiometric matrix Y corresponding to the exchange species on that emergent cycle, we got this, which corresponds to the reaction F going to W. Effective reaction, which was like F going to W. And so that cycle corresponded to what I could draw like this, something doing this. Okay. And the other one, same thing, corresponds to S going to P. And so that is a cycle doing this. Okay. So that's the meaning of Sy acting on an emergent cycle. And the flux of a given exchange quantity can be, you can read this as, can be decomposed in terms of an effective reaction acting on a current. So this is the current of that effective reaction, because many different cycles can carry the same Y species. Although in this case, only one, the sum disappears in this concrete example, as we will see very soon. So for further expressing the importance of emergent cycle, I'm going to talk about entropy production at steady state. I was planning to do it in general, but that will take too much time. So I will focus on steady state. And I want to show you that at steady state, entropy production can be expressed only in terms of these effective reactions. So how do we do that? It's very simple, because you remember that entropy production, we expressed it in terms of the chemical work minus the total derivative of this G, the free energy. If we are at steady state, the derivative of G is 0. by definition of steady state, because G is a function of the concentration. At steady state, concentration do not depend on time. And so basically, this is only the chemical work. And the chemical work was expressed as the chemical potential of the exchange species times the current of these exchange reactions. And now it is very easy. We simply add here the expression of the Y current that we have here. Forgot the vectors. And what we get is minus sum over epsilon of mu y sy times C emergence times C epsilon, like this. And what is this? This is the delta G of this effective reaction. You remember that the delta G was the change of mu due to a given reaction rho. So we had the delta G for an elementary reaction, but now we can define the delta G for an effective reaction. So that's a change of chemical potential. Every time we change, we implement this effective reaction, and it's going to be expressed only in terms of the chemical potential of the internal species. That makes sense because we are at steady state, and we saw that the cycle never changes once completed the internal species. Okay? So this is sometimes called cycle affinity or cycle force. And it is very important for understanding the meaning of energy transduction. And I will show you this on the example, because now if we calculate for our example delta G of the first emergence cycle W, we're going to get the difference of chemical potential between reactant and product. So this is mu W minus mu F. And delta, the other one is, we called it P. It's mu P minus mu S. And that makes sense, right? Because these are these effective reactions. That's what you would write as the delta G of those reactions. Good. So now let's write the entropy production for this application at steady state always. I can now write this as minus delta G. This would be the W1 times the current through the cycle W minus the delta PG of the psi P. And the second law tells us that this needs to be positive. Okay, now comes the really crucial difference. You remember that when we were working expressing the entropy production in terms of elementary reaction, entropy production was a sum of positive terms for each reaction. Every delta G flux with the minus had to be positive. So every flux through an elementary reaction needs to go down in delta G across that reaction. Well, this is not the case anymore. Now only the sum needs to be positive, but the pieces may not. And that's the essence of energy transduction. Energy transduction appears at the effective level in terms of these effective reactions. So just for the sake of the example, I will assume, for instance, that the reaction, the emergent cycle W has a delta G that is positive, negative. And this one is positive. So what does it mean? It means that, okay, so if this is negative, this is going to be positive. And if this is positive, this is going to be negative. So imagine for a second, let's do this Gedanken experiment where we only look at first cycle. This is the W one. So if the W cycle would be alone, this part would not be there. And so this is positive. So for this to be positive, the flux needs to be positive. Okay? So this means that this cycle is running into that direction, clockwise. What would happen if the cycle P would be alone? Well, this is negative. This needs to be positive, so this needs to be negative too. So this cycle would have to run in the opposite direction. But now, because the two processes are coupled by the chemical reaction network, we can actually, so as I said, this one is positive. That's the one now that's going to power the system. As I said, this should be, if it was alone, negative, but we will be able to make it positive. So now this is the key thing to have transduction. I can use the free energy released by this reaction to make this reaction possible. And the efficiency of this transduction is going to be given by minus the output, which is going to be plus, well, I can drop this one. So, so minus this, so minus is plus, divide that, so I have a minus in front. Okay. And now it is simply a trivial algebraic trick to prove that the second law imposes this thing to be always lower or equal to 1. Okay. You simply need to substitute this or this by this. And then you're going to have 1 minus something that is always positive because of this. And this is going to be always slower or equal than, smaller or equal than 1. So the second law, this translates immediately into this. So this is the Carnot bound, if you want. We are isothermal, so it's 1. Carnot efficiency is 1 now. You want me to do it explicitly? Okay. It's really algebra. You substitute in, you get 1 minus a term that is positive, so it's always smaller than 1. So the second law imposes directly that the efficiency of transduction is always smaller than 1. And you see what is happening is really that this cycle is forcing this cycle to go against its spontaneous direction. That's the essence of energy transduction. Okay. So now I put that through. You will have other applications of energy transduction in the lecture, in the tutorials. And now, but at least it gives you a nice, you see now why these emergent cycles are so important. You can express the dissipation only in terms of these emergent cycles. And how many of them there are is dictated by the topology. You see, it's crucial to identify these cycles to know how many what is the minimal set of currents needed to characterize the dissipation. Maybe I can emphasize the following. You could have guessed from the beginning that if you sum, this is kind of what we had here, that if you know all these cycles, you can express the entropy production of the network in terms of the sum of all these fluxes in and out. But the topology tells us that only 2 of them is sufficient. And this has to do with the fact that the network is such that these 4 cycles are not independent. Out of the 4, only 2 are needed to characterize the dissipation. Yes? Yeah. No, because in that case, you get an additional term, which is the change of free energy. And you need to decide if you want to allocate this as a useful output or maybe as an input. You may burn some G by going down in order to produce to power some reaction to go into one direction. So the concept of transduction, you will talk about that, can also be generalized beyond steady state by taking into account the amount of energy stored into the chemical reaction network. Yes. Yeah, because this is a rate of entropy production. So this is per unit time, and these are fluxes, so they are also per unit time. No, so this will also be something that we will see in some cases, which are called tightly coupled systems. These 2 fluxes are the same, so they cancel, and then you don't need the fluxes to make a prediction about efficiency. In general, it's not the case. So in general, the fluxes enter into the efficiency, and then you need to solve maybe your dynamics or to have access experimentally to those fluxes to know what is the efficiency. Yeah. In general, the efficiency depends on the flux. Maybe just a side comment for the StatMechie people, if the others, it's not so important. But if you want to make connection to Onsager coefficients close to equilibrium, you need to expand these currents into both, because each of these currents depends on both forces. Then you get this as a linear expansion into those forces, and those coefficients are the Onsager coefficients. But that would be only valid close to equilibrium. This is an expression that is valid far from equilibrium because the fluxes can be nonlinear functions of the forces. Okay, let's go to conservation laws. I know I was told to write a bit below. They are also important. And they are now the left null vectors, I will label them by lambda, of the stoichiometric matrix. Okay? So again, linear algebra tells us that the number of conservation laws is the number of species minus the rank of S. And why do I call this a conservation law? This is easy to see. If I take a closed system, I can define the quantity, the concentration L lambda as this vector multiplying the concentration vector. So you can think of this as a combination of species. It's a certain combination of species. And this is conserved because if you take the time derivative of L lambda, L is independent of time, so it acts directly on the concentration. So the derivative of Z is S times the flux. So you get this. And we just said that the definition of this, of L is that it's a left null vector, so this is 0. Okay, so this is a combination of species that are conserved by the dynamics. I will give you the example in just a second after I introduce the unbroken conservation laws. So now let's open the system. The unbroken conservation laws are those conservation laws that are still conservation laws of the open system. Okay, so now Sx is the relevant matrix because we open the system. So when we open, these are the internal species. So the number of unbroken conservation law is the number of X species of internal species minus the rank of Sx. And this, something that Francesco is going to also illustrate in the exercises. It's important, this is a physical thing. You don't see it mathematically. It's a physical statement. There is always a conservation law that corresponds to total mass in a closed system. Because if your stoichiometric matrix is well constructed, you account for all mass in your system. So once you start adding the first chemostat, so that would be the first line here, once you go from here to here, you're always going to break this conservation law. So the first Y species that we add is always going to break a conservation law. That's a statement that is physical. I cannot show it easily mathematically. This is a physical point. And that corresponds, it's going to be a conservation law that has elements in all molecules because it corresponds to total mass. And I'm saying that because this is the reason why adding the first chemostat will always decrease NS. So if I have here, how many species do we have? 4, 8. When I go from 8 to 7, I actually know that I'm always going to break a conservation law. So there's going to be one less unbroken conservation law. And this is a way to argue that this is going to be, as we remember, we also said that the rank of Sx is always smaller than the rank of X. So it's not too difficult to see that algebraically that this, because of the statement of the breaking of the conservation law, that the first one, that this is smaller than NL. But probably the simpler way to see it also is that, let's draw it here. So the conservation law is a vector. You know, as you're acting, as you're doing this has to be equal to 0. So now, as you're gonna decrease the size of this matrix, this might not anymore be a conservation law of the reduced system. Those that are still are the unbroken one. Those that are not anymore, we will call the broken conservation law. I use again this notation with the set. So of all conservation laws, there will be the ones that are unbroken and the ones that are broken. The unbroken one, it's kind of obvious since they still need to be conservation laws of the reduced system. I can always write them with zeros here. I can extend them in the full space by this later. It's going to be always, yeah, because here, formally, strictly speaking, this is defined in the X part of the space, but I extend it to the full space like this. So there are 0 in the Y part of the space. Okay. This is simply because this doesn't count. Yes, so let's now prove what happens when we look at the dynamic of a broken conservation law. So the broken, I can first do the unbroken, even though it's kind of obvious. ddt of this. For the reduced system, it's LYU, okay, yeah, LYU times concentration Z. Derivative. I replace now by the dynamics. So it's going to be S times J plus LYU times this. Now, this, sorry, by definition, is, yeah, I don't need that. Because I'm working in full space, so I can work in full space, but I know that this is 0 in the X part, so here I can put Y and Y. I just argued that this is 0 in the Y part. So this is 0, and this by definition, LU, not by definition, but since LU is both a conservation law of X and of the full S, this is also 0. And so this is 0. So the unbroken conservation law is conserved even in the open system. But the broken conservation laws, they are not conserved anymore. So I can directly jump to this. Lambda broken times S times J plus L lambda broken in lambda IY. So this is still a conservation law of the full. So this is still 0, but this now is not 0 anymore. So this is different than 0. And so if you want, the balance equation is that the way in which this conservation law changes is by minus Ly lambda B I Y. And we can now look at our model application. So let's go back to this guy. A new check. So first statement, this is an unbroken conservation law, this vector that I'm drawing here. 1, 1, 1, 1, 0, 0, 0, 0. Now do the test. Multiply S. You do this. You take S and you multiply it by that vector here, and you will get 0. And you see, I have all zeros in the Y part. This is why it's an unbroken one, because it works if you do this both for S and for SX, both for the full and for the reduced. In both cases, you're going to get 0. Now let's look at, there are 2 broken conservation laws in this system. Okay, the E I put here. This one, which is 0, 0, 0, 1, 1, 0, 1, 0, and this one LF 0, 1, 1, 1, 0, 1, 0, 1. So this, you can check that they are conservation laws of the full S, but not anymore of the SX, not anymore of the open. So they are conserved in the closed system, but as I open the system, they are not conserved anymore. Yeah, I'm sorry, I cannot do it on the blackboard because my arms are not long enough. But you can check that it works if I didn't do any typo. But if Francesco is not complaining, it's okay. Now let's look at what a bit their meaning. So LE, it's the sum of the 4 first species, which are these ones, E, EF, EW, EF. So what do you think it means? Okay. Can somebody tell me the EEF? EEF is EW and ES. Yes. FS. Okay. So this is saying that, not for nothing, we call this E, because you can think of E as an enzyme. It's something that is always inside the system under different form, but it never gets exchanged even when you open the system. E never exits the system. It's called the moiety. It's a piece of the molecule that always stays inside the system. Let's look at LS. I look on my, you can check it. So this is the concentration of EFS plus P plus S. It's unfortunately that I'm so far from my drawing, but EFS plus P plus S, look at the graph. What you can see is that you can think of these pieces as being conserved in the full system, but not anymore in the open system, because now that piece of molecule gets exchanged with the surrounding. And let me quickly write the last one. LF. This one is longer because it has many. So EF plus EW plus EFS plus W plus F. And here, please check. So F converts into W. It's the same molecule if you think of it in terms of conservation. It gets F again, W and F. So this is F can convert into W, but doesn't convert with anything of F. This F gets transformed into W, and W gets spit out. So you can think of F as a piece of molecule that may change conformation when it goes from F to W, but it's the same piece. So that's the meaning of these conservation laws. And they are encoded in the stoichiometric matrix. And just to finish the application, you can, since we said this is E This one is conserved also in the full system. This is 0. The S1 is now exchanged with two fluxes, IF and IW. I'm applying this now. Okay. And the last one, no, sorry, this was the F1. This is the F1 and this is the S1. Because they are broken when I open the system, meaning they start being exchanged with the surrounding via those fluxes, the yellow flux. I see some, oh, Simone? So this was conserved, these two quantities, they were conserved in the closed system because these pieces of molecule, they always stay inside the system. If you apply reactions, they're never going to change. The last one.
Yeah,
yes.
These are broken, right?
These two are broken.
Yeah. So I understand the second, but I don't understand the third, because if, let's say, now I don't see the numbers, but the reaction EW going to E occurs in the closed system, wouldn't that quantity change?
Yeah, but in the closed system, this is always conserved. So you can convert a F into a W. So you do -1, take any reaction, look, F goes to F, nothing changes. Now F goes to W, I do -1 + 1. That quantity doesn't change, right? Because I do -1 in F.
So maybe the thing is confusing, like, let's say you do EW going to E.
EW going to P.
E.
Ah, here, yes.
That one. So
yes.
the W is exchanged with the reservoir.
Not if it's closed, but
So
if it's open, yes.
What happens if it's closed? Is it?
Nothing. W stays in. So W, this plus this remains constant.
Okay, perfect. So I was confused. What happens if you close it to that W? Like,
yeah. Then if you close whatever reaction you apply, you can change the single concentration, but this sum is never going to change.
Okay,
no reaction is going to change that sum.
Okay.
Let's do the test.
I see it now.
If you, it's too far for me to show you.
Yeah, I think maybe the thing that. Okay, it's fine.
The one we had is this one. This goes -1, and this goes +1. So the full thing doesn't change.
Yeah, I think it's probably a matter of formulae. So let's take that reaction, for example, right? So in the open system, I understand it. So the W, when the transition occurs, is let's say spitted out,
yeah.
Right? But when you close the system, now you take that as an internal molecule.
Yeah.
Okay. So it's a different thing. So essentially, okay, I get it.
Yeah, it's an internal molecule, and
yeah.
So now this sum never changes. Whatever reaction, you can test every reaction.
Yeah, now it's clear. I wasn't sure what happened to that W because you didn't have it among the internal species. So
no, in the S is the matrix of the closed system. So W becomes an internal species.
Becomes an internal species.
Yeah.
That was confusion. Okay, thanks.
Good. I think I'm going to make it. But I need to cancel stuff now. What can I cancel? This I still wanted. I forgot to make an important comment, actually. Yes. Before I cancel stuff. So, yeah, I can go further here. I will combine, not for nothing, I wrote this here. that the number of emergent cycle is the of S and SS. And here, by definition, the number of conservation law is the number of unbroken conservation law plus the number of broken conservation laws. So here I didn't, yes, I did, no? Yes, it's here. These two things, this and this. So now I can rearrange this as the number of broken conservation laws is the number of, is NL minus NU, which using the two things that I crossed, NL and NLU, is going to be given by NS minus NX minus rank of S minus rank of SX. Now, the number of species minus the number of internal species is the number of Y species, the exchanged one. And the rank, this is still there, was the number of emergent cycles. So now I get something which is quite remarkable, that the number of exchanged species is equal to the number of broken conservation law plus the number of emergent cycles. What does this imply? Think of it starting from the the closed system. I have no Y species. I add the first chemostat, 1. The first, I said, there's always the first thing to happen is always that the conservation law gets broken. So 1, 1, no emergent cycle. Remember that at steady state, dissipation is controlled by emergent cycles. This is basically telling me that with 1 chemostat, 1 exchange, no way to go out of equilibrium. And now I can go further. You see how the topology is now going to tell me how I can put my system out of equilibrium. Because let's put the second chemostat. Depending on how I put it in my network, you know, 2 different things might happen. Maybe I break another conservation law. This happens, and this happens in this model. We will, I think this we will see in the exercises. Still, I'm at equilibrium. So for certain chemical reaction network, this is again, yeah, it's not intuitive because we naively say, oh, 2 chemostat, there's a difference, it should happen. No. If the second breaks the conservation law, there's no emergent cycle, you're still gonna reach equilibrium at steady state. But if by chance you don't break a conservation law, you create your first emergent cycle. And in that case, your system goes out of equilibrium. So you see how this is very important because it shows you how the topology is really telling you if what you're doing when you're adding your chemostat is driving your system out of equilibrium or not. Okay, adding a chemostat, think of it like that. I start with the matrix of my closed system, S. Okay? No exchange, no yellow arrow there. And now say I add my first chemostat. So the first one, which one is the one below? F. You need to agree, huh? F. No, let's take the lowest one so that I don't need to rearrange my matrix. The bottom one. Yeah, the one at the bottom. So now this is now my SX, and this is what now my SY, right? I remove that line. So that means you're not bringing in the F. No, I am bringing the F. Okay, let me do it like that. Yeah. So let's do it visually. I start with the closed system. Okay? My system is closed. Doesn't look closed, but it's closed. Well, now it's closed. I'm saying let's add the F is concentration. And then I'm saying, okay, what happens with this relation? The number of Y species is now 1. I broke a conservation law. I have no emergent cycle. What happens if I add the second one? I can let the second one, let's say that it's S. It doesn't need to. I could choose the other ones. Huh? I could add P. But then I need to rearrange to structure it at SS and SSY. But for simplicity, let me do S. I exchange S. Now I can predict that if that guy breaks another conservation law, I will have no emergent cycle. And actually, it's the case. I don't want to go in the example, otherwise I will not be able to finish. I will do it in the tutorial. So if you want to see it in the tutorial, I'll go step by step and show you what happens. And then it's only when I add the third one, the third chemostat, the third exchange species, that in that case, I'm going to create finally an emergent cycle. So you see how it works constructively? Let me, what do I want to erase?
Massimiliano?
Yes.
Just to confirm the sort of mechanical procedure of checking this thing. So I guess the first thing that you do is that you find the left null vectors of S, right? And then you basically then every time you add something, you add a chemostat, you just check which of those continue to satisfy this condition in the open versus the closed system.
Exactly.
Okay, and then you just mechanically do it, and if you see that one of them is now broken, then you know that now you have an emergent cycle. Right?
Yep.
Okay, great.
Well, no, if it's broken, the moment you break, there's no emergent cycle.
That's right.
It's only if you don't break that you create an emergent cycle.
Yeah, I misspoke.
Yeah, I realize it would be nice to do the example now, but it's not going to work. Let me erase this. It's sad, but I have to do it.
And if I can make another comment, I guess sort of since you were talking about topology, if you just look at the network, it's sort of, I guess, easier to see which ones would lead to cycles versus which ones would not, right?
Can you repeat, please?
Yeah, so I'm just saying, yeah, we did a bunch of nice linear algebra here, but
Yes.
one could also just cheat by looking at the actual topology of this network. I understand that in realistic cases, it would
Yeah,
get
that's the
complicated.
comment I always get. So if you want to show something to explain it, you need to make it a network simple. And so people say, oh, but it's simple. Why do I need all that linear algebra?
No.
But then if I would take
understand.
a complicated network,
Yeah.
It would be very hard. But then, of course, you would not understand anything because the example would be hard. So I think you're right.
Just to map the sort of match to what we can actually see while we can see
Exactly.
it.
Here, I think it's like an intermediate level of complexity. It's still simple enough so that you kind of could have guessed, but
yeah, so you can see that F and S will not work, but F and W will work, and S and P will work.
Exactly.
Because those lead to cycles.
But when you get like 10 reactions and 20 species,
I agree.
It starts to be a mess.
I agree.
And that's why it's important to formalize this so that you can really apply it to a metabolic network, for instance, which is what Francesco is going to do.
Thank you.
Okay, just because it makes things simpler for the calculation, I will choose a special basis for the conservation law, which is easy to explain intuitively. And it's related to precisely what I was just saying, to build things constructively, because I imagine that I start from my full network and I remove my first chemostat. Sorry, I chemostat my first species, for instance, F, in this case. And as I said, this one will necessarily break a conservation law. So there's going to be this vector that lives everywhere. And I'm going to simply normalize. I mean, it's not really normalized. I will divide it by a number such that this is 1. Okay? This I can always do. It's a vector that has component everywhere. And now I divide by a number that is this number so that I get 1 here. Good. And these are all non-zero number. I mean, yeah, non-zero number because that's the full conservation law. Now I add a second one. And yeah, just to give a different example, maybe that one creates an emergent cycle. So this one, now I have an emergent cycle. So this one will have crosses everywhere. So, sorry, since it does it, we'll have a 0 here. And then starting, this is still going to be a number. Now, let's say that the next one again breaks a conservation law. This is the second to break a conservation law. And now this is 0, 0, but I can choose it in such a way that I get a 1 here. And I could go on like that. And the point I want to make is that whenever I break a conservation law, I can always choose it in such a way that I get a 1 here. Okay? Why do I say this? Because I want to define the matrix of broken conservation laws, which contains the list of all the broken conservation laws. And I will build it in such a way that in the X space, it is something. And in the Y space, I split the Y in 2 types of Ys. The YP are those that break conservation laws, and to which I can always assign a 1 and reorder things in such a way that I have the identity in this part of my matrix. Okay? If it's 3, it would be like this. But the point is, this is the identity. It's a choice of basis. There's nothing. And YP and YF, I have the number of YP is equal to the number of broken conservation laws. Because it's every time I break a conservation law that I do this procedure of dividing to have a 1 here. So this is just saying, from a mathematical point, it's a change of basis. There is a change of basis that allows me to have the identity in this square matrix. Okay, so this is going to be the identity. This guy. Let me write it here. There exists a basis such that this is the identity. And this is convenient. And that basis, if you apply it, so as we saw that this is the definition of the conservation law. So I chose now a basis to represent that guy. In that basis, I decide to name terms M. It's a choice because of moiety. Okay, and the reason why I do that is because every time you open that Y, you know that it's going to be that species that is going to be exchanged. And so the moiety will carry that. And the example I gave you is actually precisely in that, in this basis. Because if you check, if you write those vectors as LB here, like this, this is exactly what you get. Okay, now I can show it. The RLB in the example. In the example, we had 2, and we had 0, 0, 0, 1, 1, 0, 1, 0. 0, 1, 1, 1, 0, 1, 0, 1. And so you see this is the identity. And these are, so that I chose the vectors precisely in the right basis already. Okay, so this is, now I can call this my moiety. And you can really think of it, I could make this explicit, but in my example, M be precisely the vector of the two that we have. So LF, LS.
I think we are getting lost.
Yes.
So maybe you can repeat the argument.
Yes, the argument, it's because there's really nothing deep into that. It's simply that I'm saying, you know, L is arbitrary. There's a choice of bases involved. I'm simply giving a procedure to naturally get one choice of basis. I do it constructively like I did. I add the first chemostat that breaks, I normalize to 1. The second one that breaks, I normalize again such that this element is 1. By construction, we'll have 0 here. And so when I fill my matrix of LBs, so this is, every line of this matrix is a LB. Okay, this is a L lambda broken. So these are the different lambda broken. Because I build them like this, I make sure that I have the identity in this part of the L matrix. No. And of course, we did it already. The L I gave you here are such that I'm already in the right basis. If I would not be, okay, maybe this will clarify. It's a little bit more algebra again. But there is, let's say that I would have written my L into a basis where this is not true. Okay, then what I can do is that I can define my, LBYP minus 1, that when acting on this original thing is going to give me the L, this is, B without the hat, this one, that has the identity here. So there exists a change of basis. So that this is only acting in the YP part. There exists a change of basis that takes a matrix which would be the one that I would fill with any L. So that one would not have the identity here. And if I apply this matrix on it, it will give me the identity here. It doesn't, is it clarifying? It's simply.
So maybe one thing I didn't understand is this second block. So I understand that you can make a rotation or a transformation such that the last, let's say, last
only on the last block
is an identity. But then you have an identity, you identify a second block of this matrix. That is something I don't get. That's by chance. Okay.
Yeah, I think it's what is puzzling you is that I chose there. That's the point, and that is puzzling him.
No, this other, you have two identities.
Ah, no, okay, but that's by chance, yes.
Why did you draw that line then?
Too deep, because this is LX, LYF, LYP.
Okay.
Yeah, sorry, this is by chance. So it's really only this part that is important. Okay. YF and YP. So all the chemostat that broke a conservation laws, all the chemostat that created an emergent site. And the vector that I get now are these two. I could also mention that because of this change of basis, you can also show that now if you would act yes, that would produce exactly. So if you act with this, yes. So LB acting on Z. And then I act with this inverse matrix here. Yeah, so this is the hat. And so this is my, what I called originally the L lambda in any basis that I would get. And I act with the lambda P minus 1 transformation. So I take this transformation, I act on these lambdas. So it's like I'm doing a transformation. So this is times Z, sorry. No. It's not that. Yes. Then, by definition of this, I get LB acting on Z, that is the moiety. And so what this shows you is that this matrix, that is the one that creates the identity in this block, it's also the one that takes a linear combination of the conservation laws such that I get the moieties. So you can think of this M as simply a rotation of that L. I take that L and I do a linear combination to get the M's.
And sorry, can you just clarify once more what you mean by moieties here? Just so that I'm absolutely,
yes, it's precisely those pieces of molecules that are involved in the conservation laws. Okay, that was a little tricky, but it's really not deep. And I will illustrate this in examples in the tutorial. But in the 26 minutes left, we need to do now the final point, which is, okay, I only wanted to have that convenient basis because then calculations are easier. And go back to the entropy production. And now see what we can do using these conservation laws to rewrite the entropy production in general, not only at steady state, in a way that is suitable for open to analyze open. Let's see if I can. Okay, now B, thermodynamics and topology. I anticipated thermodynamics already with the steady state one. This is because of time, but now we do it in general. Topology. And the first thing I do is I introduce a new free energy. And now we'll also understand why discussing moieties was important. We call it G curly. And it's simply the old one that we used, but this is very similar to what one does in the grand canonical ensemble. Sometimes it's also called at equilibrium. People have used this. We generalize it to non-equilibrium, the semi-grand free energy, because we now remove the moieties, which are the object that are exchanged with the surrounding. Right? We saw that these M are simply a choice of L's, and the L's were the broken conservation laws. So this is the pieces of molecules that once we open the system are exchanged with the surrounding. Okay? And this is like going from canonical to grand canonical ensemble. You know, you start, you exchange energy, but not matter. Once you exchange matter, you will have a Lagrange multiplier, that is the chemical potential, multiplying the number of particles that is exchanged. It's exactly the same here, except that the conservation laws are more complicated because it's only pieces of molecules that are exchanged. But conceptually, this is exactly what we're doing here. Yes? We call it G curly. Semi-grand is simply because as you open the system, as you add more and more chemostat, you may start exchanging even more. So grand canonical is because there's only an N, and so you directly exchange everything. Here you only exchange part of the stuff. So semi-grand. That's what. I didn't come up with that word. Okay, and what do we do now? Well,
Sorry, I'm going to ask another question. So if you do, in this analogy, if you do a grand canonical thing, you would have the chemical potential of the species in the bath,
yep,
not in the system. But here I understand mu is the...
Yeah, but let's take concentration control. When you fix the concentration of F, then it's like F is the bath, right? You're saying F is in large abundance and it has a fixed concentration. So you're basically fixing the potential of that guy.
Can you do formalism cases where you have a different chemical potential?
Yes, because for now, I don't ask you to, I only define that. I didn't do any justification. I'm simply defining that quantity because it's going to be a convenient way of rewriting the entropy production. So now I take the derivative of that thing. Okay, the first term is the derivative of J, and that one we know already. And the second one will have two terms. The derivative of the moiety, or broken conservation law, if you prefer. It's a special basis. And the second term, and that's actually related to what you were asking, because we don't necessarily assume that this guy is fixed. We allow for this guy to also change potentially. Although in most applications, in concentration control, this is never going to be the case. So this term will typically be 0. But that term is becoming important once you start injecting stuff in your chemostat, because then the concentration might go up. And then that terms play an important role if you study growth. Good. Now, I simply use what we found for the second law here. So we had that this is minus T times the entropy production plus mu times I, which only lives in the Y part of the space. And yes. Now this term here, I will use this. M is L times Z. Yes, by definition of the conservation law. Yeah. So it would be by Z, but since it's a conservation law, if it's S, this is the calculation that was just behind here. So this would be dz by dt. I replace now by the stoichiometric matrix acting on J plus the flux part. But this is a conservation law. So on the stoichiometric matrix, it is 0. So that's why I can directly put here the exchange flux. And then I put the wrong sign here. This is minus. And this, I will already define it as, so that I don't need to rewrite every time. We call it, we called it initially the driving work. We are a bit stuck now with that because when we were looking at concentration control, it's really when you drive the chemostat, the concentration of the YP species that guy changes. But in growth, as I said, it has a different meaning. But anyway, we still keep the name driving work. And so this is plus the driving work.
Question?
Yes.
Could you just please explain again what the mu YP is? This is not the, so I thought initially it was the mu of this sort of effective big moiety. So if I treat it as like a mega molecule.
Which it is, but maybe I should have insisted more on that. So when I do this procedure of adding chemostats, so I add Ys, all the Ys that break a conservation law, I call them YP. All the Ys that create an emergent cycle, I call them YF. I can anticipate a bit on the terminology. P stands for potential, F stands for force, and we will see why. Okay, but operationally, it's if that chemostat breaks a conservation law, you call it YP. You put it in the set YP. If it creates an emergent cycle, you put it in the set YF.
Okay, I see. And if there are multiple things that are breaking conservation laws, then that's why you get the vector, this mu vector, this mu YP.
Yes,
vector.
because as I go on, I may have multiple Ys, and all those that broke a conservation law, I call YP.
Okay.
So this guy is an old friend, right? This was the chemical work. We called it chemical work. This was really the entire energy that we brought into the system. And I'm now going to call this full thing the non-conservative work for reasons that will become clear in a second. Non-conservative. So let's now look at this non-conservative work, and we will rewrite it differently. So it's the chemical work minus this. I rewrite it. Maybe I can do the first operation already. I'm gonna so this is Ly. Okay, this is the Ly part acting on Iy. So I can split the I part in Yp and Yf. And I will first write the Yp part, mu Yp. Maybe I'm going too fast. Let me do it. Lyp times Iyp minus mu Yf Lyf times Yf. Yes, that's it. And remember what the whole thing that confused you all was to get this equal to 1. the identity here. So that now this minus this is all the y's, this is only the yp, so this becomes the yf. So these two things together here go here. And minus mu yf L yf yf. And so I can actually factorize this. Okay, the vector. Where? Ah, yes. Why YP now? I'm confused. I need to take distance. So wait. Why there was the YP? Ah, I'm just, so this is wrong here. Yes, thank you. Because it's only this that I'm splitting. Okay, this part is the sum. So this is YP. And now I simply can rewrite this as follows. YF minus YP. And this matrix, you know, takes now a linear combination of the YP, the potential species, with this matrix, times the current of the YF. And this I will call the non-conservative forces, YF. Okay. And remember that how many YF do I have? The number of YF is equal to the number of emergent cycles. So now, just to rewrite it elegantly so that we have everything written as the second law in the right order, before we start discussing the meaning. Now, what we have is that T sigma dot, the entropy production, is the non-conservative work plus the dry, always positive or equal to 0. So, first remark, let's, at steady state, if we do, at steady state, by definition, we do concentration control. We fix the concentration of the chemostat. So this is going to be 0 because we don't change, the driving work was here, we don't change YP. So this is only the non-conservative work, which is now the product of this force over the YF times the YF. So I was planning to show you explicitly and in general that the cycle representation is equivalent to the force representation, but I did it I did it now because before I showed you that at steady state, I could write, you remember we had delta epsilon G times C epsilon. And think of this simply as a base transformation. I can, at steady state, I can either, and the number of epsilon is the same as the number of emergent cycle. Okay, so this sum involves the same amount of quantities, and epsilon is NYF. So I'm simply saying that at steady state, you can either write things in terms of these forces and these fluxes, or cycle forces, cycle currents. These ones, let's speak experimentally. This might be easier experimentally to measure, because this gives you directly the flux that is exchanged with your chemostat. The cycles are nice in terms of interpretation because you see them in terms of effective reactions. But they might carry more than one chemostat. So it's only a change of basis. But the meaning of F as well as of delta G remains crucial. And I would say now we see again what is needed to be at equilibrium in our system. If we want to be at equilibrium, we need the force to be zero. So equilibrium will occur when these forces are all zero. And you see how it's non-trivial. Again, I emphasize this. The topology is in that thing. This is telling you, okay, choose your YP as you break the different conservation laws. And then the remaining YF, if you choose them very carefully in such a way that this thing is going to be zero, then you're going to be at equilibrium. But if you would not do topology, it would not be easy to know when your system is at equilibrium and when it is not. This is why these non-conservative forces are really important. You need to identify them to know when your system is or is not at equilibrium.
Question?
Yes?
So here, I understand that these two statements that you made over there are equivalent when the chemostat that you're connecting is a chemostat, like you're exchanging material, right? I'm just sort of thinking about instead of exchanging material, if you had light or something else, which was sort of driving these cycles, would then only the prescription on the right be the appropriate one, or the one on the left? That's what I'm a little bit confused about.
You mean this or this?
No. I mean either F dot I or delta G dot psi. If you go a bit lower into the right, you see that the entropy production can be written in two ways, right?
Yes, this.
Correct.
Yes.
So I'm just wondering which is the more appropriate description when you
this
are
is,
not.
I mean, okay, these are, it's not related to the first part. If you have light, I mean, you will have new forces, but you need to upgrade our formalism. I didn't speak about light, because then you will have thermal gradient entering, okay?
Right.
So I assumed isothermal, so I excluded light. But light will create gradients, not of chemical, not chemical gradients, not of these types, but of thermal gradients. So this is one aspect. Now this is really a matter of convenience. This is a choice of basis, whatever you prefer. We find that the cycles are very useful, you will see, to analyze metabolism, because you have this picture of effective reactions. So I like this one, but this one experimentally is important because I think in some cases experimentally you have access to that guy. Okay?
I see. Because the reason I was thinking of this was that maybe if I think about it as if I think about cycles on a sort of global scale, then it's sort of not obvious to me what the chemostat is, and so what I might have better access to is sort of some component of the cycle, right?
Yes. Okay. Maybe a comment about that. This is again a way to explain what we brought with this formalism, and I think it's a nice. It shows how we are between the two pictures that Pablo was talking about. You remember Pablo was talking about one picture where dissipation is expressed in terms of all the reactions inside the box. And we had that expression of sigma. You remember sum over all reaction, flux forward, flux backward. That's the picture where your box has all the reactions. You need them all to get the entropy production. But that's kind of tough because furthermore, they need to be elementary. So a lot of stuff. Then there's the other picture. You simply know everything that goes in, everything that goes out. Okay? Okay, fine. But that might be non-significant, right? Because it's not only oxygen, it's sugar, it's CO2 and water. If you know the topology of the network, what we're saying is that we are kind of, well, I would say, no, it's even not necessarily in between. We're giving you those currents, which is a subset of those that you need to characterize the dissipation. So if your network is a black box, you don't know anything about the topology, then you need all of these currents. If you know something about the topology, you realize that only a subset of those currents is necessary. And that might be very useful from a practical point of view. Okay? And this is this. This is the subset, because this is not all the YF, all the Y. This is only the YF.
So in this example, I think it would be helpful if you can
yes.
open out these brackets in terms of what the components actually are. What is this?
I can write it for the example if you want. Yes. So F, and again, we chose things that such that in this case, the two representations are equivalent. So what you will see is that F in our network, the FP is this, the FW is YW minus YF. Don't need the parentheses here. And the two currents that we need are YP and YW. And if you want the conservation law too, the WD in this case is going to be minus the derivative, because these are the potential species, mu F times LF, which is now the, minus derivative of mu S times LS. So you can use the matrix that I gave you here and verify this. Okay, so I think this is the big point. Now, let me also comment maybe on the fact, so this I will not show. I will ask them to copy the notes and put them online, so you will have the proof. In the same way that J was always bigger than JX, one can also prove that J curly is always bigger than JX, which also means that same thing as before, but now for the open system. Before we said if we close the system, J is going to be minimized. Now I can say that in an open system, so this is another special case, let's say open, and we call this detail balance when all the F are 0, then, and with no driving, so WD is also 0. So this is only going to be minus the derivative of G curly. Okay. So how do I do this? I do this by aligning those chemical potential in such a way that they are 0. So here in the model, I choose YP equal to YS, YW equals to YF, but my system is open. Okay, so I'm exchanging stuff. In that case, since I made those F0, my system is going to minimize G curly. And G curly is going to go down until I reach equilibrium. And you can also use this for energy storage, this other definition that we were talking about before. It's imagine that you have a system, and Francesco will show you that, where you can create a force to go up in J curly. Then you can define the efficiency as the ratio of the J, the increase of J for a given powering by the non-conservative work. So how much energy these non-conservative, the system is already open, but you start with a zero force. You turn on the force by lifting this YF, and now you're gonna curl up in the chemical reaction network via this non-conservative force. Okay, so let me just think a second. Yeah, I will stop here, but. You can also store energy via Yes, but then you need to control the flux. Exactly. Okay, so I hope I managed to convince you that topology is important for thermodynamics. You know, it comes at a little cost of linear algebra. I really recommend to attend Francesco's tutorial to see how to apply this to different networks so that it gets more intuitive, because I think these things is by example that one gets a better feeling for how it works. So I hope the message topology thermodynamics went through. It's really essential. I also hope that this message went through. This is also very important. Using topology, we can really identify which are the minimal set of fluxes contributing to dissipation. But there's this big hole now. Everything has to be elementary in terms of chemical reactions. And are we stuck here? No, this is really for biology. I mean, we kind of enter now what do we need to do to go towards biology, towards complex chemical reaction networks. And we will show how we can treat enzymatic reactions, even entire metabolic pathway in an effective way that is thermodynamically consistent. And it is essential, these notions of effective reactions is absolutely central to do that. And we will do it less technically, but really more visually. So those who were scared by this formal part, I think the next part will be easier and much more biological. And I think I said everything I had to say.
Are there any more questions?
Massimiliano, can you explain this simplification for mu y, I y, those two terms giving rise to this simplification? Yeah.
Because y, if I sum over all the y's, it contains both the yf and the yp. So this is a sum, right? This is a sum over all the y's, which I can split as a sum over all the yp plus yf.
Okay.
And so since this is the yp part, it goes away with the yp part here. Okay. And I'm left only with the yf.
Thanks for this. I really like that you reiterated this point about the internal versus external picture. And I'm just wondering, this equation that you wrote in the end, this f dot I equals delta G dot psi. So I'm just sort of wondering, if I didn't know the topology, but I knew the other things, in principle, could I back calculate the topology using this inverse relationship here, and how far can we?
Yeah,
can we get?
This is an interesting thing that we discuss a bit in the circuit theory. In principle, yes. We have never tried in practice, but it's actually an interesting strategy that by checking systematically how the fluxes, if you have all the fluxes, how they correlate with each other, you could infer things about your internal topology.
Yeah, it's just a self-consistency argument, right? Because typically I'm guessing that in biological systems, the topology is known, but not fully known. There are always uncertainties, and I'm wondering if you could prune the uncertainties in some way, guided.
Yes, I think this could be used as a way to probe the topology. We haven't systematized it. I mean, a little bit, yes. You'll show that? Ah, great.
Yeah, I guess the least you can say is about the presence of cycles.
Yeah.
Yeah.
Yeah, yeah.
Any more questions?
I'm worried that it's only the PIs that are asking questions.
Could you interpret this non-conservative work physically? So if I maintain mu p is equal to mu s and mu w is equal to mu f, then these non-conservative forces you're saying are zero, but I would still have a non-zero IP and IW.
Yeah. But your system would reach equilibrium in that case. It's not trivial. So in other words, you don't need to equilibrate this chemical potential with this one. It's the key is this with this one and this with this one. But these ones can be different and these ones can be different.
So supposing I was to interpret that particular circuit as really, so F is a food, W is a waste.
Yeah.
Right? And conversion of food to waste is being used to drive the production of product P from substrate S, right?
Yeah,
Supposing
this was the transduction example that I gave.
Yeah, so supposing that's what you were doing.
Yeah.
Then you could do it without doing non-conservative work, right?
No, I would always get, because this term here would contain the sum of the two. So the non-conservative work, the non-conservative work would be these two forces, right? Yp minus Ys times the current Yp plus Yw minus Yf times Yw. So if this is equal to this and this is equal to this is zero. There's no more non-conservative work. If you want to transduce, if you want to use this term that is very positive to power this one that is negative, but such that the sum is still positive by the second law, you need, the sum will be non-negative. Yes.
Supposing I'm able to get a non-zero IP, right? Which is that I'm able to produce P while still keeping, these F's zero, right? Mu P is equal to mu S and mu W is equal to mu F, right? Can I get a non-zero IP?
No, because as you turn off this and this, these guys become linear functions of this and the currents vanish too.
But that's something else. That's not contained in these equations, right?
How
do we see that? How do we see that IP will go to zero if these guys go to zero, if these forces go to zero?
Because, wait, let me think what is. Because if these guys go to zero, entropy production will be zero. And all the fluxes have to be zero for entropy production to be zero.
Well, your, it's only the W dot NC term that is zero.
But remember the form of the entropy production in terms of sum over all currents. We saw that every elementary reaction needs to go to zero for the entropy production to go to zero. Remember sum over, we had it as J rho minus J minus rho log J rho over J minus rho. Sum over rho, this was the entropy production. So if this has to be zero, all the currents through every reaction need to be zero, and so every current will be zero.
Yes, so
that's one way
I'm
to
not,
show it.
I don't care about entropy production going to zero.
Francesco wants to say something? In the transient, yes. Yeah, at steady state, yes. So at steady state, this needs to be an equilibrium steady state. Sorry.
Maybe I'm not able to articulate. I don't want to take up everyone's time, so maybe we can talk about it later. But my main concern was that I want to have a non-zero IP. That's my goal.
Yes.
in that whole circuit, right?
Yeah.
I want to have a positive IP,
Yeah.
right? So
But
can
positive,
you tell me whether I can? So what does it take to achieve a non-zero IP? Is what I'm interested in, because that's what I want to do.
okay. But do you want to specify the sign of this?
So I'm just wondering from this, and from whether it's needed. I mean, can I still do it with mu p equal to mu s and mu w is equal to mu
Yes,
f?
of course. So let's assume YP part, you remember this was this. This is, let's ignore this part of the network, okay? We only look at this. So there's no coupling to this. Only this part. If mu s is larger than mu p, the flux is going to flow like this. And this is what this second law tells you, because then I don't have this. And now the second law applies to only this. So this times this needs to be positive. So if this is positive, this has to be positive. If you want this negative, this has to be negative. Now the interesting question is, if this is alone and this is positive, but I want this negative, this alone cannot happen, right? Because otherwise I violate the second law at the level of only that part. That's why now I need to add this other part of my chemical reaction network. Because now if that part is more positive than that part is negative, then this process may occur. So it's really the coupling. It's, of course, you can create a current but it will always alone, but it always go downstream to the force. If you now want to create a current against the force, you need a powering mechanism. And that's the powering mechanism. And it's the network coupling. It's this intermediate reaction here. That's the key one that is coupling the two processes. Is this reaction here that couples the two processes. And you can think, by the way, of this as a molecular model. Because this is kind of, think of E as an enzyme that binds different things, catalyzes it. So this can be thought of as a simple model of a molecular model.
Maybe I can, so if I understand the concern is that essentially this equation tells you what can be done and cannot be done, but you can't use it. So these fluxes will be some complicated functions of this chemical potential, and it won't tell you what the value of these fluxes.
Yeah,
right?
it tells you that it may be possible, but then you have to check whether kinetically
if you really want to compute these fluxes, you need to solve the entire thing.
Yeah.
So.
But this you can, you have the equation of mass action law, etc. So if you construct your model, you can really study efficiency of transduction even at finite power. Model, you can do it. If you have experiments, you can do it. But it's true that the argument I just made is generic. I can say that it may be possible to do it, but it doesn't mean that that model does it.
Here, thank Massimiliano again for the very nice lectures.
Thank you.
And we go off for lunch and are back here at 2 o'clock for the presentations by the attendees.